All right, so I think oh, great. We're ready to get started. So we're very happy to have our last speaker of the day, who's Yuanyuan Feng from Penn State University. She's going to be telling us about dissipation enhancing flows and applications to Kuramoto-Szymanski equations. Thanks, Yuanyuan.
Okay, thanks. Thanks, Cecilia, for the introduction. Also, thanks the organization community for organizing the nice conference and letting me to present my work here. So today I'll first introduce the dissipation enhancing flows and then talk about the applications to Kuramoto-Szymanski equations. So, okay, so first let's look at the energy decay in scalar transport. So suppose theta satisfies advection diffusion equation. Here, theta may represents the temperature or density in a fluid, and here V is the advective flow, which is divergence free, and the kappa represents the strongness or diffusivity. In our setting, we always assume periodic boundary conditions, and the initial data is restricted to be mean zero. Since V is divergence free, so Poincare inequality would give us the L2 decays at a rate of e raised to negative kappa times lambda 1 t. Here, lambda 1 is just the principal eigenvalue or Laplacian operator. So can we do better estimate? Can we improve the rate? The answer is yes. So if exponential decaying rate can be improved as e raised to negative kappa times h kappa, where h kappa goes to infinity as kappa goes to 0. Here, h kappa can be explicitly written through sufficient mixing flows. What is sufficient mixing flows? I will introduce later. So, okay, let's look at the upper bound. So the trivial upper bound can be obtained from the basic energy estimate, which is e raised to negative kappa times lambda 1 t. If we define the dissipation time tau star in this way, here tau star is defined by the smallest time, such that after such amount of time, the energy always decays to 1 over E of the initial energy. So clearly by the definition, we can see the L2 energy is bounded by e raised to negative t divided by tau star. So this is from this comes from the definition of the dissipation time tau star. And from the basic energy decaying here, we can see that we have a trivial bound for tau star. So tau star is bounded by 1 over kappa times lambda 1, or we say tau star is of order 1 over kappa. And if we have better tau star bound, then that would of course implies faster exponential decay rate for the L2 energy. Okay, so now let's look at the dissipation time bound. So as I just mentioned, we have an elementary bound of tau star, which is 1 over kappa. In 2008, by the work of Konstantin Kislev et al. In 2008, they proved that if V is time independent, then kappa tau star goes to 0 is equivalent to saying that the transport operator without grad has no eigenfunctions in H1. Such flows are called relaxation enhancing, and weakly mixing flows implies relaxation enhancing, but not conversely. Here, they give no information on the rate at which kappa times tau star goes to 0. For us, together with my advisor Gautam, in 2018, we proved that if V is mixing with rate function h, then tau star can be bounded by kappa 1 over kappa times h kappa. Here, h kappa is some function which can be solved from this formula. Here, h we can say capital H can be obtained from little h. Explicitly, if little h is taken to be exponential decaying, then we get tau star is bounded by c divided by kappa to some power delta at first, and later we improved this to be C times log kappa square. So at the same time, Tarek and Michaela in 2000, they also proved that if H is exponentially decaying, then the bond for tau star is also bounded by log kappa square. Here, so okay, recall the definition for the dissipation time tau star. We can actually obtain the L2 energy decays like e raised to negative C times T divided by log kappa square if V is exponentially mixing. So is this rate? So is this the optimal rate for tau star if V is exponentially mixing, or say if log kappa square is the optimal rate for tau star? We cannot answer this. Our guess is that it is not. We guess the optimal bound should be C log kappa, but we cannot prove this currently. So, okay, similar result also holds if the diffusive term is replaced by Laplacian. So, okay, then what is the mixing rate, H? So, okay, let H be the flow map of V. If V is mixing, we actually say that if for a function f which is mean 0, then f composed with the flow map goes to 0 as t goes to infinity. Since V is incompressible, it implies that the norm of f composed with the flow map phi is conserved. So that means the f composed with the flow map phi can only converge weakly to 0. So mixing means for any f and g in L2, the inner product f composed with a flow map phi and g should contain the inner product goes to 0. So what's the mixing rate? Mixing rate is the rate at which the above convergence happens. So let H be the rate function, which is positive, decreasing, and disappear at infinity. So if V is mixing with rate H, that means this quantity, the inner product, is bounded by H times some norm of F times some norm of G. Here, the norm X cannot be taken as L2 norm. If X is L2 norm, then since we recall V is incompressible, so the L2 norm is conserved. So L2 norm can, if X is L2 norm, then here the H function can only taken as 1. So we have to use stronger norms. In PDE, we usually choose H1 norm. By duality, this actually tells us that the H-1 norm of F composed with the flow map phi is bounded by H times H1 norm of F. So flows are called dissipation enhancing if the dissipation time is of order little o of 1 over kappa. So we can see that relaxation enhancing flows introduced by Constantine and Kislev in 2008, those flows are dissipation enhancing. Also, mixing flows are dissipation enhancing. However, regular mixing flows or ellipsis mixing flows with exponential mixing rate are not easy to construct. The more regular the flow, the harder it is to mix the tracer optimally. Other flows like shear flows, for example, shear flows is the flows like Uy0 or planar helical flows. In 3D, we call like such flow Vx1, x2y. The planar helical flow are defined by Uy times sine y, Uy times cosine y, 0. For those kind of flows, the corresponding transport operator V dot grad has a large kernel. For example, if for the shear flow Uy0, if the function f, or we say if the density only depends on y, then the transport operator V dot grad would have no effect on the density. However, dissipation enhancement can be obtained by projecting out the kernel. This okay, so one can read the work by Benjosin Cotizilati in 2017 or the work by Wei in 2018 for reference. So why are we interested in dissipation enhancing flows? Because it has a lot of like useful applications. It may prevent finite time blow up due to concentration in K-Lisigo models. This has been done by Kislev and Xu, He and Benjosin, Hope and Rijogo, and also by me with Shi and Wang. It may stabilize the flow for invested damping for Euler. This has been studied by Benjosin, Masmodi, also Benjosin Cotizidati, and many others. It may also prevent phase separation, like in Canhillier model. This has been discussed by me together with Yu Feng, Gautam, and John Luke. It may also ensure global existence for the model of flame front propagation, like Koromoto-Shwarzynski equation. For this, I will discuss in details later. So, okay, so now let me just briefly introduce the Koromoto-Shwarzynski equation. So I think in the first week of the conference, David has gave a very nice introduction of the Koromoto-Shwarzynski equation. So today, maybe let's just do a brief review. So Koromoto-Shwarzynski equation is a model for long wavelength instabilities in dissipative systems. For us, we study the problem in 2D or 3D periodic box. Here, L1, L2, or L3 adjust the length of the periodic box in each direction. So for this equation, for Koromoto-Shwarzynski equation, so we usually look at the two forms of the equation. One is the integral form, which is phi is a scalar, it's partial t phi plus a half times grad phi square equals minus Laplacian square phi minus Laplacian phi. And for the derivative form, if we denote u as the grad phi, then we get partial t u plus a half times grad u square equals minus Laplacian square u minus Laplacian u. So this is a dissipative system with Burgers type nonlinearity and which has instability at large scales. Even in 1D, it's non-trivial. There are a lot of challenges in the analysis in 2D and 3D. We listed this in below because there are unstable modes for linearized operator if any period Li is greater than 2 pi, and due to no maximum principle, since it's biharmonic, there are no a priori L infinity bounds. Also, there are no energy identity since the integral of u dot grad u squared dx is not 0. So there are no a priori L2 bounds also. So, okay, our result with Anna says that if there are no green modes Li less than 2 pi, then we have global in-time existence of mild solution for small data in L2. And these results can be extended to LP with P between 1 and infinity. If there are green modes, we can also achieve global in-time existence for any data in L2 if the dissipation enhancement flow V is added. So we add a flow V to this equation, and this V is dissipation. Here, V is a given time-dependent divergence-free vector field, which is also dissipation enhancing. So this model, actually this advective Kuromoto-Shevardnadski model has been raised. It was raised by Dandekar and Collins in 1995 to model passive flame propagation in premix combustion. We prove in both cases we use the continuation criteria are based on L2 norm. So our result says that for any initial data phi 0 in L2, then there exists a mild solution phi of the advective Kuromoto-Shevardnadski equation, which satisfies a uniform in time L2 bound, provided the dissipation time of V is small enough. And the bounds on the dissipation time tau star can be explicitly computed in terms of the size of the initial data. So here I'll list the strategy of the proof. So we project onto the mean zero functions correlate psi. The mean of phi is not preserved, but can be controlled. We then prove short time existence of mild solutions of psi of the projected advective Kuromoto-Shevardnadski equation in a suitable adapted space with data in L2. We prove that this psi is also a weak solution in L2H2 for any T positive, satisfying and also satisfying an energy equality. Then we show that if the dissipation time of V is small enough, there is a priori exponential decay of psi, L2 norm, the L2 norm of psi. And then we conclude using the continuation principle based on the L2 norm, the global existence of the solution is achieved. Okay, so how about we use some other flow V? So we know that mixing flows are not easy to construct, and they usually mixing flows are time dependent. So we hope to use some steady shear flows to this apply the steady shear flow to the equation, and we also hope to get global existence. So this is a joint work with Cotizilati, Dossi, and Anna Mazzucato. So how does this work? So we apply these shear flows to the equation. We get such shear flows are dissipation enhancing in some space, and the kernel space is one-dimensional. The component in the kernel space of the flow can be reduced to a modified one-dimensional Kuromoto-Shevardnadski equation. The L2 norm have uniform in time bound in the absence of green mode if L2 is less than 2 pi. And for the component orthogonal to the kernel, the L2 norm is bounded due to the property of the dissipation enhancement. So here are the details. We decompose the function in this way. For any function in f in L2, we let the f average to denote the average of the function in x direction, and we use f not equal to denote the function f subtract the f average. So then the advective Kuromoto-Shevardnadski equation can be decomposed as these two equations. We see here phi average satisfies, phi average is a one-dimensional equation, and this equation is like a one-dimensional modified Kuromoto-Shevardnadski equation. Here we have like some coupled term, which is not coupled. This is a nonlinear term coupled with, there is also a nonlinear term coupled with phi not equal and phi average here. for the equation of phi not equal, it satisfies okay, the equation here. And we can see here in this equation, we have the nice operator uy dx plus v Laplacian square. So this operator is good. It has the dissipation enhancement property, and which may result in the global existence of phi not equal. So how to prove this? So if we denote h nu as a transport operator here, okay, so if the transport operator in the transport, so in the linearized operator, if the diffusion is Laplacian, this has already been studied by Bedrosian and Cotizilati. They proved the rate of dissipation enhancement using hyperellipticity, and also it is studied by Wei. He used some Gilhart-Proust criteria for M-accretive operators to obtain the dissipation enhancement rate for this operator h nu. In our case, so we have the bi-Laplacian operator here. That the method is but the similar method should also work. We use the Gilhart-Proust criteria for the M-accretive operators and get the decay rate of this operator is bounded by e raised to negative t times nu times m, nu to power of m divided by m plus 4. So what is m? M is the order of critical points of U. So since M is the order of critical points, so the best rate can be achieved is when we take M equals 2. The best rate is actually C times e raised to t times nu to 1/3. So, okay, so I will conclude my talk with the application in the 3D. So in 3D, we also hope to construct some nice and simple flows, which enjoys nice dissipation rate, and the kernel space is one dimension. So first, we know like in 3D, the shear flow would not work, since in 3D, the kernel space of the shear flow is two-dimensional. So if we reduce, so since the kernel space is two-dimensional, for the two-dimensional Kuromoto-Sharansky, we cannot. It's difficult for us to obtain the global existence. So we hope to construct some other flows. So here we introduce the 3D planar helical flow. So it's defined like this: Uy sine 2 pi y divided by L3. Uy, the second component is Uy times cosine y 2 pi y divided by L3, and the third component is just 0. So we prove that the global existence of solutions can also be achieved when linearly growing modes only appear in the direction of the planar helical flow. Or it equivalent to say like L3 is less than 2 pi. This is a joint work with Shi and Wang. So to prove this, we first studied the rate of dissipation enhancement for such flows, and we apply this flow to the advective Kuromoto-Sharansky equation, and the global existence can be obtained. Another application of this flow is we use such flow to Taylor-Segal model, and we prove that in 3D, this if we add this flow to the Taylor-Segal equation, global existence can be ensured without the initial 8 pi restriction on mass. Okay, I think okay, this is the end of my talk. Thank you. I think I ended like 5 minutes earlier.
All right, that's great. Thanks, Yuanyuan. Let's thank her for this very nice talk. Does anyone have any questions to Yuanyuan? I hope I'm not pronouncing your name too wrong.
Yeah, it's good. Yuanyuan, yeah.
You're kind.
Hi, can I make a question?
Sure, go ahead.
Okay, thank you. Thank you for the talk. I have two questions. The first is more concerned with the first part of the talk that we always talking about
The dissipation.
age little that the rate of the mixing when the flow had a rate.
Yeah.
So I was in the paper that you wrote with your advisor and also with the professor Anna. I see that typical examples are always exponential decay and polynomial decay. I
Yeah.
mean, yeah, I was wondering if there is another decay that is interesting from a point of view of application or something like that. I mean, I know that this h little had to be a decreasing function and vanish at infinite, but uh, there is another kind of decay that is interest
So
because
usually, like people are interested in the exponentially decaying function rate, right? Since
yeah,
that's the best decaying rate we can expect.
yeah,
Well, you
double,
can, if
yeah,
I may, you can have perfect mix in infinite time, right? So it can be a line that intersect the axis. But it has to be rougher, of course.
yeah, but that is impossible for the
No, that is possible. There are
for
explicit
the
examples. Yeah,
I
you
mean
can
I mean
definitely, yeah.
I mean for the vector flow that are h1. I mean,
No, not H1. You have to be below. You have
okay,
to be below L1 in time with values in BV. So say like Holder continuous, for example, or okay, not
yeah,
L1 in
because
time.
I was trying to construct another example. I mean, I would take h other function. I mean, not polynomial, no exponential. I don't know if that makes sense. Well, thank you. But the other question was more related with the end of your talk that you say that 3D helical flow can be also applied to killer seagull. Uh,
Yeah.
I was reading a little bit about the modified killer seagull that the kernel is considered to any dimension to be the logarithm. And my question is, do you know something about this? Because there is present also the dynamics, for some special data that is brought up. So maybe be a suitable system to suppress the blow up with a suitable vector field. I mean,
So what's your question? You mean like in some
my question is if you take not killer seagull but modify killer seagull. I ask you only if you read about this because in modified killer seagull the kernel is changed to be the logarithm between the distance for any dimension.
so you want to use this apply this flow to some modified kilo-segal model, right? So for that modified kilo-segal, do you still have the like what do you know about the existence?
I know that there is blow up for a small initial data.
Yeah.
So I was thinking that maybe it is possible also to suppress that blow up by suitable, not necessarily this planar helical flow, but a small enough dissipation time, vector flow, vector field.
Yeah. Okay. I can expect like if you apply some nice flows with small dissipation time, it would suppress the final time blow up. Here, why we use the planar helical flow? Because this flow is simple and easy to construct. It's time independent. It's very simple, and it has a nice effect. So, for the normal Taylor-Segal equation, like a lot of people have studied this, like Kessler and Xu, they use some relaxation enhancing flows, and later Jacob and He, they use some shear flows to deal with. But for the shear flow, it only works in the 2D dimension. For the 3D case, they still have the 8 pi mass restriction.
Yeah. In modified Kessler also have this 8 pi restriction. So it seems like probably works. Okay, thank you. That was my questions. Thank you for the talk again.
Okay, thank you.
Thanks. If I may, there was also one comment in the chat that Gautam said concerning the rate of decay. He mentioned about rates of the form exponential to the minus t to the sum power alpha. So just in case it's relevant to the discussion.
Yeah, thank you.
That's in response to his question. So sorry a lot for sending that chat message in the middle of your talk. It's Tone's fault. He said he'd never met you when you're at Penn State. So my apologies. I didn't mean to distract you. But I just had 2 comments. One was in response to this last Keller-Segal comment, right? As long as I think whatever kernel you put, as long as it's some sort of diffusive operator, if you put like, I don't know, fractional Laplacian to some power, as long as the power is bigger than 1, you can have this notion of dissipation enhancing there and still make it work out. You just need the diffusion to be stronger than the convection. If that power is lower than 1, then okay, I give up. I don't know what to do, right? If it's more, I think you're in business, right? But I had a question, I guess, which I just realized from what you said about this Donkey-Weiss Gerhard-Pruss estimate. I don't know if you can use this. I guess he used this to deal with the dissipation enhancement of shear flows. Yeah. Can you also use it to get dissipation enhancement of cellular flows, but with not with Laplacian, but with like maybe bi-Laplacian, right? Or some fractional powers. Because cellular flows with Laplacian, I know how to do, but I need maximum principle. If you give me 2 Laplacians, I don't know how to do it. And if you know how to do it using this Donkey-Weiss technique, that would be very cool, right?
So actually, we thought about that, but you remember, Yuanyuan?
For cellular flow, yeah, but we haven't. Yeah, I think I don't know. I think there would be some difficulty.
So that with the shear flow, you can go to you can apply the Fourier transform in one direction, and that makes the estimate more manageable. But if you have now a cellular flow, you can't do that. Well, anyway, I don't see how you do that. So, but yeah, we thought about that, but we didn't manage.
Just a small remark. If you were here in my talk, I replaced Laplacians by something that is not Laplacian, right?
Not Laplacian. Like what?
Like Landau.
Oh, yeah.
And without doing everything in Fourier, you can still get the same in hand displaces. I mean, that was the whole point of my talk last week.
Yeah, I was at your talk, but
yeah, but so it didn't help me because the thing I used was maximum principle. The thing I used to prove it for cellular flows was maximum principle, and your trickery still doesn't help me, right? But I don't know. I need to look at it again, right?
Mm-hmm. Yeah.
There is time for a little question.
Yes, it's the end of the day, so you're free to ask any other questions.
No, that emerged just now. I was wondering if taking advantage of these shear flows, have you construct an example of a sequence of vector fields with a small as we want dissipation time? I mean, I know that there is a result for the Professor Gautam that they probabilistic approach, that they construct a sequence of vector fields. You put a dissipation time and you can get less than that by a probabilistic approach. But has been explored these shear flows to construct such a sample or arbitrarily small dissipation time vector fields. I don't know if I was clear, sorry.
How to do what? Can you say that again?
Okay, I wonder, there is, if I gave you a positive number delta, can you give me a vector field that have a dissipation time less than delta?
Yeah, of course.
Yeah, but this relies on the construction of the article from Professor Gautam, that is a probabilistic one. My question is about that shear flows that like sheets, horizontal and vertical. Do you know if there is a construction using this kind of vector flows to get arbitrarily small dissipation times, vector fields?
So you mean other than shear flows, can we get some other flows that can achieve arbitrarily small dissipation time, right?
Yeah, it's because I work only from one construction. I mean, I just for me. I was wondering if there is another one, because their one was a little bit difficult to get to understand. But if no, it's okay. I understand.
So for cellular flows, I think Gautam has proved that like they can by constructing some cellular flows, which has arbitrarily small dissipation time.
Okay.
All right, maybe I also want to give the opportunity to anyone who wants to leave the room. So before anyone does that, let's thank Yuanyuan again for this very nice talk.
Thank you.
And if anyone wants to ask any other questions, you're free to stay more in the room, or we can just resume for the day. And we're our last day of the workshop is tomorrow. It's going to be at 10 a.m. local time.
Yeah, so just let
Oh, sorry, and there is one announcement that Annie wants to make. Yes.
Yeah, so the first talk was by, it's supposed to be by Sara Danetti, but she's not feeling well. So we canceled the first talk. So actually tomorrow we're going to start with the Taufik Hamid talk at 11:20 Brazil time.
Yes, might be good, since there's a lot of people who are not here, to maybe send an email about this, right?
Yeah, sure.
Yeah.
Thank you. And you can stay in the room and discuss if you want. No problem.
Bye, everyone. Yeah. Bye.